The broadcast is now starting. All attendees are in listen-only mode.
Good morning. Welcome to this morning's research results presentation from the Ohio Department of Transportation's Office of Research. This is Victoria Beal. I'm with the LTAP program, and I'll be the host for today's webinar. Today we have for you computer vision-based pedestrian detection technology demonstration and testing using CAVe-in-a-Box tool. And your presenter is Sai Bantu. The webinar this morning will have a handout that's in the handout section. And if you're not able to download that, don't worry, because we will also send a link out to it after the presentation concludes. Also, we encourage questions throughout the presentation, and I will be doing my best to stop our presenter and read those questions to him as they come in. So please feel free to use the questions box to submit questions throughout. We are attempting to record the webinar, and as long as we're successful, a link to the recording will also be shared with you once the webinar has concluded. With that, I'm going to go ahead and turn things over to our presenter. Are you ready, Sai?
Yep. Thank you, Victoria.
Thank you.
Hello, everyone. Thanks for taking time today to attend this webinar. I'm going to talk a little bit about my research using computer vision-based pedestrian detection technology and the Federal Highway Administration developed CAVe-in-a-Box tool. Go ahead and get started. At a high level, we're going to discuss a few research problems touching on which aspects of problems that we are going to tackle using connected and automated vehicle education in a box, and then some background, traditional solutions, infrastructure-based, that are applied to solve those problems, and then discuss some new methods that are being researched and deployed at this time to solve those research problems. I'll also discuss the research methodology that we deployed or implemented in this research project, and then a few simulation and experiment results to validate that methodology. And I'll discuss some results and ideas for implementation, along with a key component of this research, which is contributions to smart mobility workforce development. So the first problem that we started looking into is kind of imagining yourself crossing the street, and how would you actually feel if there's a busy traffic, a lot of vehicles around you. So one such problem has happened near University of Cincinnati. In 2022, there were 2 students who were hit by a speeding vehicle. It was quite emotional for the whole university at that time because it was a stolen vehicle, ran over a couple of students, and one student was killed at the spot. And I'm sure you all have similar kind of stories that you have been through where someone you know or somebody that you've seen was hit in a traffic crash because of a speeding vehicle, for example, the one that you could see here. Some of the traditional methodologies that you could see are message signs to kind of slow down the drivers, in particularly as an aftermath of such crashes that have happened. And you can see how they have installed pedestrians in areas, slow down as safety alerts and message signs, which is after the crash has happened. But just to dig deeper, one of the nonprofits have actually tried to study what are the speeds looking like in that particular intersection where the crash has happened. So the study was conducted almost a couple of weeks after the crash has happened. Speed limit on Jefferson Avenue near University of Cincinnati is about 35 miles per hour, and about 400 and 130 vehicles of 150 to 1,000 vehicles. So roughly 2% have recorded more than 40 miles per hour. And what that means to vulnerable road users using the streets is the fact that, as National Highway Traffic Safety Administration, NHTSA, has identified, as the speed increases linearly, the fatality and serious injury risk to vulnerable road users using the streets increases exponentially. So that is a significant impact on people's safety on streets as the speed is increasing beyond the speed limits. The second problem is how our traditional traffic signals kind of operate. This is an intersection in the city of Atlanta. You could see that there is a walk signal that's red, vehicle signal that's red, pedestrian crossing not allowed, vehicle turns not allowed. So it's kind of a safe situation at this point. But you could see where people may take decisions to start walking based on their judgment that vehicles may not be entering the crosswalk. They would probably double check, sometimes maybe in a rush, checking their phone, try to cross the street with their own judgment. But you could also see when there is walk signal is green for pedestrians to cross the street, vehicle signal is also green, so vehicles can take a left or right turn. So at this point, there is a conflict between vehicle trajectory and the person who is using the crosswalk. Just to kind of show it on an animation perspective, you could see how vehicles could take a left turn or a right turn and potentially be in conflict with people who are crossing the streets. I know traditionally, most of the times it's up to the driver's judgment to go slow or fast. Sometimes person on the street is rushed, sometimes driver is rushed, but these are all human factors that come into the play due to these unavoidable conflicts at our intersections. What that kind of looks like is something similar to this. I would like to play this one more time. And the reason is that you could see two things here. You could see the conflict happening between person who's crossing the street and the vehicle taking a left turn. But you could also hear that the person is not actually using the crosswalk. So they're just probably just a few feet away from the crosswalk, just trying to cross the street while it's green for the person and also green for the vehicle. So that these conflicts can keep happening and can potentially result in a crash or a near miss, which is another statistic that the researchers have been looking into. The third problem that this research has tackled is how to prepare our future workforce with all the technologies that are evolving in transportation. So as kind of mentioned by USDOT, Intelligent Transportation Systems, Professional Capacity Building Team, ITSJPO, and PCB teams, preparing our future workforce is very important in two ways. One, to be able to, better the traffic safety with them being drivers, but it also improves our ability to solve these problems using technologies and how can we consider smart infrastructure or smart mobility to help benefit both people in the vehicle and also people on the streets using different modes of transportation. Traditional solutions, I would like to actually ask you guys if you have or if you know how would you solve problems like these, please feel free to drop a message in the chat. We'll happily visit if you have any questions or any ideas on how you would solve with existing infrastructure or technologies that you are aware of. From our research, what we found was there are traffic calming solutions. There are speed bumps that are installed, raised crosswalks, rumble strips, or protected bike lanes. Several flashing beacons have been installed, as you can see some here. Rectangular rapid flashing beacon or pedestrian hybrid beacons are very common. But most of the times they do require large-scale investments and need some infrastructure changes, road closures, and many times these are fixed timers. So they're not really adapting to traffic or traffic change. Peak hours, I'm not sure if there's a set pattern that's recognized because of weather changes in different states. So many times it's fixed timers. And more importantly, there's lack of data to validate true benefits on how they are improving pedestrian and driver safety on streets. New methods that are evolving in this space are computer vision and AI for detection. So with the advent of AI, what happened more importantly is that now we have better semiconductor technology where we could deploy these AI models and see how they can detect and even send a message or react to something or get the data in real time using semiconductor technology that can be used to deploy these AI models now. There are several particularly focused on pedestrian detection that are being developed. Some are open source, some are proprietary, but they do have some limitations, which, for example, you can see here, there is some poor performance in low light conditions. Potentially, if you're using it for really, very close to the persons, there could be algorithmic bias due to skin color. You could also see occlusion in detecting really large groups of people. We don't know whether occlusion is bad or good in that situation, so I think it depends on the camera mounting height at that point. Moreover, all these sensors detect and pass some really raw metadata to the user, but not necessarily provide a real-time connectivity. So which, again, that goes into a different paradigm, which is communications. So going into communications aspect, we know that Federal Communications Commission regulates all of the communication-related activity between states and the United States. And in 2020, what FCC did was they issued a report and order which adopted rules to limit 5.9 gigahertz spectrum, a part of the 5.9 gigahertz spectrum, to be able to use for intelligent transportation system operations, which is vehicle to vehicle or vehicle to infrastructure kind of communications. The commission actually proposed to, initially there was DSRC based technology. So it's time to transition into cellular based vehicle to everything communication. So from moving on from a short range communication to more long range and better speeds in cellular vehicle to everything technology. Equipment in DSRC include onboard units, roadside units, and the OBU is a trans receiver which is mounted in a vehicle. The roadside unit is a device that's mounted at the intersection. I'll be right back, but meanwhile, if you have any questions, please drop them.
Go ahead and put any questions you have for the presenter in the questions box, and we will read those off to the presenter as soon as he returns.
Great, I'm back. Thank you. Yep, so those are two main devices that are used in establishing that communication between, for example, the sensor, which could be a camera, and then a driver who is in a vehicle, for example. And then moving on, in recent years, much more recently last year, USDOT has released a draft plan how to accelerate V2X deployment and kind of created a draft action plan so that state and local agencies can start referring to them as they deploy some of these technologies that are available. Short-term goals, in fact, include to transform 75 metro areas. At least 25% of those signalized intersections should be transformed into V2X enabled intersections is one of the draft action plan goals that USDOT has. And then obviously there are several connected vehicle pilots that are deployed, which have proven success in deploying and testing these vehicle to everything messages. The CV2X platform does offer, as the cellular technology keeps evolving from 5G to 6G, CV2X does offer that ability to upgrade to a better network as they keep coming available wireless technology. Meanwhile, the standards that are being used to transmit the actual message, for example, camera says a person is detected at such a lat long, and how could we translate that into a proper V2X message that can be transmitted to roadside unit and then transmitted to onboard unit, and then onboard unit deciding whether to generate a threat alert for the driver or not. So that is being done using some Society for Automation Engineers standards. J2735 is one such standards which has been traditionally used, but there are much more innovative standards that recently came out 2022, which is J3224, which is sensor data sharing for cooperative driving automation. So that's going to be really key in testing some of that standards, really understanding how these how pedestrian detection can actually translate into an alert at the vehicle. Some of the investments that have been done recently, if you have been aware, USDOT launched a really nice grant program, and recently 3 states have been awarded with approximately 20 million each to actually deploy CV2X technology in some of the intersections and potentially develop an action plan or even a strategy how to scale this technology at a federal level into other states, so that local and state governments can start using this action plan and these references to to start deploying some of their technology in transforming intersection safety, particularly when there is a vehicle VRU conflict, as such an example that I've taken in this research. CAVe-in-a-Box, which is a great initiative by Federal Highway Administration, is a great platform for practitioners to learn what this technology can do, but also conduct some field tests on evolving technology. So I think it's a great platform that could be utilized in both ways. And also, it can be used for training the next generation workforce, which I think has been a great component of this research project as well. Some cutting edge research that has been done. I think University of Tennessee Chattanooga team has done a great job. They have recommended Tennessee DOT in a research project that they have done based on the results that they have developed. They have used CV2X to enable a vulnerable road user collision alert system, which establishes bidirectional communication between pedestrian user devices and the roadside infrastructure. So between mobile phones and the infrastructure to generate hazard warnings or improve situational awareness. I think the other aspect of this cellular vehicle to everything is traffic management in general. So if there are connected vehicles, there was a simulation study that was done by Virginia State University for Virginia DOT to kind of simulate how if vehicles start using this CV2X communications, how can that translate into fuel savings? So they have found about 14.7% fuel savings if 50% of connected vehicles penetrate into Los Angeles downtown traffic. So in this study, based on all the literature review that we have done, now we have started thinking about, okay, there is existing infrastructure like traffic signals, and then there is upcoming technology such as CV2X. So how can we use both of these to really develop an architecture so that we can improve vulnerable road user safety with near real-time technology that's available to us? So the research methodology is, I could divide that into 5 different segments. The first one is basically understanding what sort of computer vision technologies are out there that can detect people in real time, and how can we acquire one of them. The next step is to really develop an architecture to integrate the sensor to the connected infrastructure, such as roadside unit in our case. Finally, developing interfaces, software interfaces, to translate the messaging that's coming from the camera or the sensor and inputting that into the CV or V2X format for the roadside unit and onboard unit. So that interface needs to be developed. Further downstream, we develop the actual real-time pedestrian detection and transmit messages to OBU, and that solves the first problem, which is to generate real-time safety alerts for the driver. The second part is, can we use similar architecture to start adding leading pedestrian intervals and potentially dynamically extend ped walk phase if a vulnerable road user is detected crossing the street. So we started looking at that, which could potentially reduce vehicle vulnerable road user conflicts and improve vulnerable road user safety in such conflicts. So we took that 2-pronged approach to solve those 2 problems, the first 2 problems that I identified in this presentation at the start. So required components, we have acquired several hardware components and then started integrating them. On the left side here, you can see that there is a V2X hub, which potentially can be deployed on a Raspberry Pi. And then on the right side, we used Coda Wireless software development kit to generate an SDSM message. So we were trying to understand how a personal safety message kind of looks like and a sensor data sharing message kind of looks like, to compare and contrast how these messages can impact safety on streets. Finally, there is a mobile kit that was assembled, again, with an onboard unit connected wirelessly to an Android device. And then the Android device is pretty much resembling a dashboard in this use case. So test kit assembly. So we have assembled the infrastructure kit that you can see on the left here, which is the CAVe-in-a-Box, which is connected and automated vehicle education in a box. You can see that there is a traffic signal controller, a roadside unit, V2XR computer, which is a Raspberry Pi in this case, and a network switch to connect all these devices to the same subnet. Finally, we also acquired a signal head and a walk signal to be able to showcase the benefits of some of the research outcomes in this study. To the right, you could see the mobile kit, which can be, in this case, particularly it's connected wired so that we could see some of the messages, but it can be installed in a vehicle so that we could, so that the driver can see those alerts as they're generated. So key research outcomes are mainly 5, starting with a framework for such real-time safety response system. Secondly, a hardware-in-the-loop simulation to really understand how these interfaces have performed. So we have developed a software interface to integrate the computer vision detector with roadside unit. Now we wanted to make sure we did a simulation to validate that the interface is working well, and we did troubleshooting and completed that development. Next, we actually took the whole equipment into the field to validate that this real-time safety response is working well. And we chose a non-line of sight intersection to really simulate something like a downtown intersection where there are buildings around us, tall buildings around us, and how could that impact such real-time messaging. For that, to validate that outcome, we have done human-in-the-loop simulation first, and then vehicle-in-the-loop experiments where humans are crossing the street and vehicles are trying to take a left turn or a right turn. Finally, we have done some sensitivity study in different weather conditions, different field conditions to understand how the system performs. So we measured the performance of the system by testing it under different field conditions. Finally, to really understand, can this similar framework be used now that we have a signal controller as well? Can we demonstrate something like a leading pedestrian interval or extending the ped walk in real time if the detector says it detected a vulnerable road user in the crosswalk? So those 5 research outcomes are realized in this research project.
Sai, we have a question that's come in.
Yes, please go ahead.
This individual would like to know, does this research look at off-nominal conditions? And they put in brackets, construction sites, bicycles locked to nearby infrastructure, vehicles traveling the wrong way.
It's a great question. I would like to take the example of the vehicle we used in this study. Some of the vehicles recently have, I guess a lot of vehicles have navigation system. And one of the tests we have done in this study is taking the vehicle in the wrong way to the same crosswalk, which I'll show a video clip of. My vehicle started warning me I'm in the wrong way direction. So it's quite fascinating what I think automobiles are developed with technology for safety, while from an infrastructure level, they still need some support from the intersection infrastructure to tell them or communicate securely what the infrastructure or the intersection control system is actually looking at. Could be traffic signal timing and phasing and timing. Could be bicycles or other infrastructure that's logged or stuck. There could be potholes. There could be a mattress on a lane. How could we really understand? So I think we haven't looked into all of that. We focused on detecting people, bikes and wheelchairs and things like that, but we haven't looked at other types of objects that could be seen as a potential alert. But yes, construction zone, work zone, I think all those object classes, I would say, can be trained in the camera sensor so that we could get relative information and alert the driver. But all of those can be explored using this framework. Right. Do you have any more questions, Victoria?
Not at this time.
Cool. Thank you. All right. So moving on, what is the framework that I keep talking about? So let's say there is a crosswalk and then a signal head, a signal controller, and a ped signal. So this is our traditional intersection. Let's say this intersection is now equipped with a camera detector and a roadside unit for that matter. So in this case, the assumption is that the intersection is in the field of view of that camera. All of it is pretty common for us to see. Now a person has entered the crosswalk or waiting at the crosswalk, not yet entered. So at this point, we could actually, now that the camera is connected to the signal controller, based on the detector output, we could trigger or program the signal controller with a leading pedestrian interval. What that does is it gives a head start for the person first to enter the crosswalk. What that does, again, is it increases the visibility of the person in the crosswalk for the vehicles that are taking a left turn or a right turn. So traditionally, 3 seconds to 8 seconds is kind of a guideline that NACTO has provided as a good safety measure for increasing the visibility of pedestrians in entering the crosswalks, so that the drivers can see them clearly and then slow down. So that increases safety of the person. We could also, the next stage is actually the vehicle is now trying to enter the same intersection. So vehicle is waiting to try to take a right turn, and the vehicle gets a green signal too. So now the vehicle is trying to take a right turn while the person is still crossing. So this creates that conflict I keep talking about. So at this point of time, now that the camera is connected to the roadside unit and the interface that we have developed is in place, assuming a personal safety message or a sensor data sharing message can be generated at the roadside unit and then transmitted to the vehicle onboard unit. So the onboard unit receives those messages constantly and then takes an educated, or it actually has an algorithm to calculate can there be a threat that is possible. If there is a threat that's possible, generate an alert. So how does that kind of looks like in a process flow? So detector looks at object that has entered the field of interest. If it is, then is the object class vulnerable road user? To the question that came through before, this object can be something else if that's of interest in a particular intersection based on the problem. In this problem, we chose person or a bike. And then that information now is translated into a sensor data sharing message format. And this software interface that we have developed is actually deployed in the roadside unit itself as a Docker container. Happy to explore that if you have specific questions on that one. But in the roadside unit broadcasts these SDSM messages to the onboard unit now. And the onboard unit, again, generates an SDSM message or a basic safety message as a feedback loop that it has received, or whatever the vehicle position is, speed is, all that information can be sent back as a feedback to the roadside unit. But within the onboard unit, there is some threat monitor logic. What that does is based on the configuration parameters, such as bore sight, velocity and acceleration, time to impact calculations, is the trajectory heading of the person is equal to the vehicle heading. So that gets analyzed, and if the threat monitor logic reports that it's a high priority and it should be alerted, then a threat alert is generated and deployed on the OBU HMI in our use case, but in future it'll just be a dashboard alert. So the first step, or the first outcome of this research is being able to test it in a lab environment. As you can see here, we have a CAVe-in-a-box infrastructure and mobile kits kind of connected wired at this point. They're not wireless. There is GPS connectivity that's required. So you can see those sensors hanging out of the window to be able to provide that time synchronization between the roadside unit and the onboard unit. And we have a CODA software development kit simulation that would show an alert that's generated. And what we have done here is we chose an intersection at University of Cincinnati to be able to showcase this research outcome. So we simulated a driving profile of a vehicle taking a left turn that you can see here, and a person crossing the street because there is actually a crosswalk on campus Green Drive near University of Cincinnati. So we recorded a person crossing as a simulated data, created a driving profile, and we wanted to see if that generates an alert. And that did generate an alert on our onboard unit Android HMI in this case. So that was our first success, and I would like to quickly show you a quick video clip on how that looks like. So the vehicle is taking a left turn, and as the trajectory is heading towards the simulated person who's crossing here, you can see an alert that's generated. The next step is to do more data collection, actually take it to the field location. So this is the test site we have chosen at University of Cincinnati, where vehicles take a right turn to enter the campus into the Woodside Drive, and then take a left turn into the Campus Green Drive. And then there are two crosswalks here. We chose the first crosswalk as it's closest to the parking lot, which is where we have set up our equipment. So the view from the parking lot kind of looks like this. So as one of our lab mates who's walking, showcasing how pedestrian and vehicle interactions kind of look like at this particular intersection. So you could see people who could potentially use the crosswalk, and then vehicles and shuttle buses, which could take a left turn. So as I said, I've shown you some of this equipment before, where we have taken it to the parking lot, where we have access to power, so that we could do some field tests. The view that you have just seen, where a person is crossing, is actually the view of where the camera is mounted at this point of time. It's not the ideal height, but it does simulate something like a non-line of sight intersection, such as a crosswalk, a crosswalk in a downtown, for example. Just to show all the components that we have set up in the parking garage to be able to test the overall system in the field. Just to focus a little bit on the mobile kit, seen this before, so let's get through. So what we have done now is, previously we had a simulated driving profile, and then a simulated person profile walking the street as well. So now we replaced the person data with a real person who's walking the street, and then we used the same driving profile to see if the alert is generated. So you could see in this particular, you could see a person walking the street here, and then you can see an alert that's being generated because we wanted to simulate what that alert looks like. So in this simulation, you can see an alert on the simulation itself, but you could also see that alert on the HMI that we have used, which is the Android tablet that can be connected wireless to the system. Just to dig deeper into the results of what we just saw is, first of all, we created a vehicle taking a left turn at University of Cincinnati Campus Green Drive. And then you can see a message that's been an SDSM message that's been generated at the roadside unit. So it's receiving the vulnerable road user data, the object, its location, speed, heading, and then it transmits an SDSM message to the onboard unit, where the onboard unit has this threat monitor logic that analyzes the heading of the vulnerable road user, its location, and then if the priority is high, then it sends an alert to HMI as an icon and also a beep. So there is a WAV file and also a PNG file that's being generated, which is displayed on the HMI as an audio and visual alert. As a third and last step for these tests, we have installed the mobile kit in the vehicle. So you could see the antennas on top of the car, and you can see the onboard unit on the driver or passenger side of the vehicle. The infrastructure stays at the parking lot so that it can continuously see the intersection, detect people, and send that information over. So there are two tests that I'm going to show you results of. The first test is vehicle taking a left turn, and the next test is approaching straight into the mid-block crosswalk in this use case. And this is the test I was talking about, where we actually drove in a wrong way, and my vehicle was able to alert that because it has navigation in it, it does recognize it's a wrong way. So the first test result, I'm going to play this video clip now, where I'll try to take a left turn. You could see my colleagues walking in the street, and I would get an alert. I'm sure you have noticed that there are a lot of alerts that are coming through because we did increase the bore side We opened up configuration parameters so that we could receive as many messages as possible, because that was one of our first initial tests. This is the second test approaching straight into the crosswalk. Obviously, the onboard unit comes with a configuration which can be configured in such a way that it can be fine-tuned for a particular intersection. There is also something called a map message that can be created for this particular intersection. If that map message is created, which is pretty much drawing a digital infrastructure of this intersection, then only the vehicles that are approaching that crosswalk in certain direction will receive the alert. Not all of them does. They will all receive the SDSM messages, but only a few drivers who are approaching the crosswalk in certain direction can receive the alerts. So it can be configured in that way. Finally, as I mentioned, we have tested it in different conditions. So this is a test during night, and we expanded the zone to capture as many people as possible that are entering the crosswalk, because not everybody uses the crosswalk as we have initially discussed. So this is to show both driver's perspective at the bottom and the camera perspective at the top, so that we get a better understanding of how this alert kind of looks like. And then one more test, and I'll probably play this one more time just to give you guys a better understanding of true benefits of this system. There are a couple of things that have happened in this video, which was coincidental, but I think kind of reiterates some of the benefits, and it was also a good experiment for us to really understand how these messages really work. So the first thing I wanted to show was where you have two people entering the crosswalk. Initially, with camera configuration parameters, we were seeing occlusion issues where two people are detected as one. So we have fine-tuned the camera to be able to, improve its performance in detecting two different people who are walking side by side. That's the first thing we did. The second thing is during night conditions, we have seen some detections and shadows playing a huge role in how people are detected. Mirror reflections from this building have also had impact on detection. So we fixed all the detector level calibration parameters. And the next step is you could see that there was some rain that has occurred just before we did this test. So the visibility is not too good, although this is a great intersection with nice light. But you could see how this could be, there is rain and you have your wipers on, suddenly your visibility is not that great. But the camera is actually has a very good view of the intersection. So that's another use case of CV2X technology, or this particular research project, where the driver may not have great visibility, but them to be able to receive this alert, where infrastructure or intersection control system has a better view of the situation. If that communication can be established, it's beneficial. The third thing that I wanted to play out is towards the later part of this test, you could actually see that an e-scooter is approaching my vehicle from sideways. And obviously we are transmitting as many messages as possible. But you could also possibly see an advantage where the current existing automobiles have sensors at the front and the back. They do not really necessarily alert you as vehicles are approaching sideways. So in this particular use case, I was able to receive an alert. And actually, I was surprised to see that somebody is approaching me at a higher velocity from sideways. So this technology can also support in that way, because intersection sees the whole holistic view of the field of interest, let's say. Feel free to throw in questions as you have, but I'll keep going on how this impacts the problems that I have identified. The first problem I touched on was the safety, vulnerable road user safety. We have identified, or we have seen that there are vehicles that have gone beyond 60 miles per hour, which are dangerous speeds. So this is the same study that I've shown in the first slide, where about 400 and 130 vehicles, which is about 2% of a weekly traffic, have gone beyond 40 miles per hour. About more than 4,000 of them are between 40 miles per hour and 60 miles per hour. So that constitutes to 99% of vehicles that have gone higher speeds. So there are some outliers who have gone beyond 60, but they are just less than 1%. So what does that mean to the solution that I just developed is the fact that if this solution is deployed, what we have done is based on driver's reaction time to the alert and then the vehicle dynamics, how much time or how much distance is required for the vehicle to come to a constant stop if they're going at higher speeds. So we used a chart that's published by NACTO to compare the range of this alert to what's published as a reaction time stopping distances. So based on that, this solution can actually support up to 58 miles per hour in a non-line of sight intersection, which could be a downtown, for example, or in this particular case, we are in a parking garage with one more parking garage and a tall building ahead of us. So this solution can provide up to 345 feet stopping distance, which translates up to 58 miles per hour. So if a driver traveling at 58 miles per hour sees this alert, that driver should have enough time to come to a constant stop before hitting that person. Ideas for implementation. The second problem is the vehicle and vulnerable road user conflicts, as I've discussed, where there is a conflict between person and vehicle because they both have a green signal to enter the crosswalk area. So required components are, in this case, we used MHCarbon Connect ITS to send detector calls to the signal controller. And then signal controller has been programmed with a leading pedestrian interval. So what that kind of looks like is when a pedestrian is detected, you could see that a pedestrian call has been made in that phase. And then when walk signal and vehicle signal are green and the pedestrian is still detected, we could extend the timer until the vulnerable road user crossing is complete. So it will stay in that phase. Imagine a situation where there is a wheelchair, and if we could detect that wheelchair and extend the timer, it will benefit that person to cross the street. Finally, when the vulnerable road user crossing is complete, then it will go into the clearance timer, and that's where you would see the flashing hand with a timer on it. The third idea, which is also a big component of this research, is to be able to engage young learners in demonstrations and training them for future workforce in transportation. So we have engaged students in demonstrating the benefits of this technology, not only at the signal controller level, as you can see a couple of students emulating how a vulnerable road user crossing looks like at Aiken New Tech, which is a school in Cincinnati. And we have actually contributed 2 lesson plans focusing on traffic light simulation and connected and automated vehicle on a desktop level, which is a great exercise for students to really understand what vehicle to vehicle and vehicle to infrastructure communications look like. Several partnerships have been established to be able to achieve this point. We have engaged more than 200 students with the support of the Gaskins Foundation and Partnership for Innovation in Education. Obviously, Drive Ohio and ODOT have been a great support. From a technology standpoint, Coda Wireless, Wash, MHCarbon, and Pathmaster have been super helpful. We have engaged, as I said, more than 200 students from summer camps to actually going visiting to schools and engaging them hands-on on the demonstration level, and also putting their hands on these RC vehicles that you can see here, where the RC vehicle spins its wheels when it's green signal, slows down when it's yellow, and then stops when it's red. All of these educational aspect or lesson plans that we have developed will end up in Drive Ohio's Educator Toolkit that will be released. The higher education toolkit will be released very soon. Should be able to search for it, and you'll be notified when it's released. This actually plays a huge role. What we have developed in this research plays a huge role in translating how these younger students, 5th through 8th grade students, understand transportation technology as they grow into college level education. So ITSJPO has several modules. For example, they have a module on understanding signal controller. So the traffic light simulation lesson plan that we have put together actually translates into how signals work in the intersection, because the traffic light simulation have the lesson plan asks students to act as roles. So a person is a signal, a person is a push button, things like that, where they understand how traffic signal work and how safety can be established. The CAVe-Lite lesson plan translates into connected and automated vehicle education in a box level stuff, which is probably undergrad level. So high school students, as they play with these Raspberry Pis, open source software, which is the V2X hub, as they try to understand them at high school level, they should be able to easily catch up a lot of that when they start reading about connected and automated vehicle education in a box at the undergrad level. Some of the pictures to show how these demonstrations look like.
There's some questions in the question box if you have time.
Yep.
Okay, the first one is, to ensure your proposed system is working, is it requested that every vehicle needs to have OBU installed? Any other options for vehicles without OBU, for example, wearing via mobile app?
That's a great question. I know that I'm probably blanking out on the application name. Travel Safely, I think. There is an application which I think probably Alert or a couple of other companies are working on, which does the job. It uses a certain cellular spectrum to be able to send that message. I think there are ways in this particular use case or for this system to work. Yes, OBU needs to be in the vehicle. And the hope is that in future, most of these vehicles will have OBU incorporated in these vehicles.
Next question. Does detection depend on presence of pavement markings? And then in brackets, they put, cannot detect crosswalk if brick/decorative or crosswalk is unmarked, ? And then at the end of the bracket, it says, does the quality of pavement marking diminish the ability of the sensor to detect the crosswalk and signaling from OBU?
Great question. I think the background does not impact it as much. And the reason I say that is the camera sensor is looking for features such as 2 legs, 2 hands, and head on the top as a person, and it's going to classify that as a person. If there are wheels, then it's going to look for a bike. It also looks at the velocity and the object size that's detected, and it has to be in motion. So as long as the object is in motion, it detects that that object. So for that, with that, I wouldn't say background such as the pavement marking has a huge impact, but I could see how if the pavement marking has a graffiti on it, or if it's too flashy, I could see how that could actually impact detection accuracy in general. But that's a study that needs to be done.
Another question. What are the benefit costs of the proposed method versus the traditional methods? For example, retiming the signal or new phasing plans, etc.
Great question. We haven't done a lot of benefit cost analysis on this one. I would say from an operations level, at least from what I worked with, the signal controller, and I'm not a traffic engineer, I'm an electrical and computer engineer. So it didn't seem like a huge challenge to integrate the detector to the signal controller and even program it with leading pedestrian interval or adding or extending the timer of the walk phase. It didn't seem like a huge challenge, but if it has to be done, I guess along a corridor, I could see how the expenses can stack up. And from a benefit standpoint, I think a human life translates to several $1 million according to NHTSA. So I think we could quickly do a benefit cost analysis, and I don't know if there is anything that we could put on a life. So, but that's a good study. I think it's a great point. Thanks for asking.
One other question on the detection of bicycles. Have you looked at programming in the new e-bikes that may move faster than the traditional bikes?
That's actually a great question. One of the things is that it looks at the velocity before classifying, or it starts with a class and it could actually change as the velocity of that object increases. So for example, if a person walking right next to the bike could be detected as a person to start with, but as the person starts riding, that could change to a bicycle, for example. Whether we could classify e-bikes versus regular bikes. It's not something that can be done at this point because they look similar. But can we classify objects that are going at a higher speed? Yes, I think we get the metadata because we have the speed of that object. We should be able to use that data to be able to generate an alert or even show it on a dashboard how many bikes have gone faster than some speed, for example.
Great. That was the last question for now.
Great. I'll wrap up my slides. I think I have maybe 5 or 6 more slides to go. All right, this is a demonstration that we have done at University of Cincinnati summer camp, where students were participating in real. We created a mock crosswalk where they were using the street, kind of, and how that translates into pedestrian counting, as they could see, and how connected and automated vehicle education works. We have also collected some assessment results to really understand whether students understood what we were trying to say. So you can see from some of the results here, I'll probably read out one question from the summer camp where we asked the students how would they describe their current knowledge of connected and automated vehicles. And before we did any engagement, you could see 65% saying not as much interested, but that translated to 72% saying they're somewhat familiar. And you could also see where we wanted to generate a thought that there is a career pathway in transportation. 62% said they did not consider a career pathway, but that translated to 41%, that reduced to 42% approximately. And similar assessments have been done in other studies as well. But we also try to understand if students were gathering the information that we were trying to explain them, such as vehicle to everything. You could see where 51%, I don't think they got it right that V2X stand for vehicle to everything. But after the engagement, which is about 20 minutes or 15-minute engagement using the CAVe-Lite RC vehicle module on the desktop, and that reduced to 34% after the engagement is done, where they actually understood what V2X means from a literal standpoint. Usually, I would actually have people work on the CAVe-Lite module to see how that looks like. It excites even adults how the RC vehicle starts spinning its wheels as soon as it's green signal, and then slows down when it's yellow. But as some of the questions have come through, this technology can be applied for other vulnerable road user subclasses. Most off the shelf cameras come with pedestrians, bicyclists, and trucks and vehicle classes. But I know for a fact that there are several e-scooters that are coming through, skateboards, one-wheelers, wheelchairs, strollers. All these can be vulnerable road user subclasses. So it's important for this research to continue, where we expand these classes and start generating alerts based on which vulnerable road user class it is. We could also track vehicle and vulnerable road user conflicts and near misses to alert pedestrians using smartphones, which is an idea that was discussed as well. And we could also detect firearms, and potentially, I know Bosch has a new feature about firearm detection based on audio and video. That could be an alert too, I guess, to the emergency response system. Research implications, several implications. The first one being obviously prioritizing vulnerable road user safety on our streets, and then enabling that connectivity to understand how people and vehicles are interacting with each other. Then the next one is actually understanding multimodal traffic, how different modes of transportations are interacting with each other. Can we collect that data? Can new AI models be generated or developed to enhance detection and classification? Finally, how does this actually impact mobility hubs where people meet and greet each other, or even it's an intermediate stop between your start and destination? And the other, I guess, wing is, can e-commerce deliveries or reducing carbon emissions, can they be impacted as well? So some of this framework can be implemented to study all of that. Finally, obviously the workforce development has been a key component of this research. So this research can be used as a module for engaging young learners right off middle and high school level students and train them to be future workforce in transportation. And that concludes my presentation, but I have a few acknowledgements to give. Some of the highlighted references here are publications that are outcomes of this research. Our research team included myself and Vaishak Neeraj, who are graduate students. John is an undergraduate student who developed his own CAVe-Lite during this project. Dr. Arthur Helmicki and Dr. Victor Hunt at University of Cincinnati are co-advisors and professors at University of Cincinnati. I wanted to thank Nick and Rich at Drive Ohio for being a great technical advisory committee members and supporting this research. Dan Heel from Coda Island has been great help. Scott Morse from Pathmaster has been heavily supportive of our research. William Martin, Animesh, and Safak, the whole Saxon Lab team has been very helpful. I visited their facility and was on several calls with them to be able to achieve all these research outcomes. Finally, thanks to all the partners, and I am ready to take any questions you have.
Great. There's no additional questions at this time, but they could be typing them in, so we'll give them a minute or two. Oh, one just popped up. Have you considered looking at vehicles running red lights at an intersection and triggering alerts for cars or pedestrians crossing, lights approaching the intersection?
That's a great question. It's not considered in this research project, but I have thought about it. I think one of the biggest challenges is how can we use infrastructure sensors to send a message on an alert to vehicles, one thing. The second thing is, can we use that information to send alerts downstream to other vehicles from that point, which are not in the field of view or not in the range of the intersection? So that's where I think vehicle-to-vehicle communication kicks in. We haven't studied that in this research, but I know that's a very interesting topic and should be studied further.
Okay. We'll wait and see if any other questions come in for just a minute or two. And I also wanted to thank you, Sai, for being one of the more popular presenters in the poster session for my TRB committee, the Standing Committee on Workforce Development and Organizational Excellence this past January at TRB. I know that we really appreciated having you there and that there was a lot of great engagement. So,
Thank you.
I'm not seeing any additional questions come into the question box, so we'll go ahead and wrap things up. Again, thank you so much for joining us, and thank you, Sai, for the great presentation. And please look for an email with, oh, one more question did come in. How far is the distance that messages can be transmitted?
Great question. I don't think I have that slide in this deck, but from a study that Oakland State University and Michigan State University, along with Qualcomm, based on in a highway, I think CV2X messages were ranging from 1,000 meters, I think, because there aren't a lot of obstacles and it's line of sight kind of mounting. In non-line of sight, where use cases such as you have a vehicle, a truck, and a vehicle, and the vehicle is trying to communicate with each other, like passenger cars, for example, and you have a big semi-truck between them, so that's a non-line of sight kind of situation. So the range reduces to 600 meters, I think, from the study that I've seen. And I think what we were trying to do is much more specific because of research limitations, and also maybe in downtowns where there are buildings, that can impact that range as well. So we saw up to 100, 105 meters, but also limited based on the RSU mounting that we have. But if it is mounted in a line of sight, which is what we are exploring as an extension to the study, I think the range increases to, I don't know, I'm thinking somewhere between definitely higher than 100 meters and probably less than 600 meters.
Great, thank you. So everyone who is on the webinar will receive 2 emails, one with a link to the presentation PDF and also hopefully a link to the recording. And then you'll receive a second email probably a day or 2 later with your certificate of participation. Thank you for joining us, and I hope everyone has a wonderful rest of their day.